Well, ladies and gentlemen, good morning and Assalamu alaikum warahmatullahi wabarakatuh. Pointer. So, well, friends, this is the fifth talk of series of lectures in Indonesia. So, we will enjoy several discussions, mathematics, algebra in general, and some other things also. So, this is purely research-based talk, and this is what my expertise. So, I will discuss some portion of my research, derivations, series, and algebras. And really glad to be here, and it is because of the support of Museum and Algebra Society of Indonesia, and most important is Professor Inda because her support and her invitation is very important, and I am here because of her. So I'm really glad. So, friends, academic friends, and dear researchers, the topic of my today's talk is one kind of derivation specialized on thematic derivations and its related math. Very interesting because within the symmetry, if you're talking about the symmetry, so it has a lot of meaning, not only in mathematics, but the other areas like geometry and sometimes we call in computer science how to use scope. So this is totally I'm talking algebraic point of view, not other point of view. So in fact, derivation in rings has several kind of observation. Okay, sometimes we will move on if you consider two types of algebra, commutative and non-commutative, then the things are not same as the others. I again ask everyone, Pushpanda, everything is okay? Like our voice is clear? Hello, Pushpanda?
Yes, sir. Voice is clear. We can hear you.
Okay, good. Make sure so you will enjoy the fact. Okay, so let me move slowly, and then so these are the today's agenda. We will discuss accordingly the motivation towards this new idea of derivations, then background and definitions, and then we have the kind of symmetric derivation, because now we're talking on the symmetric derivation, so there is again this area kind of symmetric derivations. So symmetric bioderivation, sigma derivation, then symmetric sigma bioderivation, generalized bioderivation, generalized sigma tau bioderivations, and then we talk symmetric and derivation, the extension of derivations. Again, generalized and derivations, then some other type of conjugate derivations. And finally, we will conclude some problem based on this thought and thought. So let us move one by one. These are the papers. The first paper already many of you know because this I've done several times. And then the second paper is important, two results concerning symmetric bioderivations. So this is what the talk is based on first, second, and third, and finally we'll go to last two. So this is the not new idea. I think more people are familiar with the idea of derivation in rates. So I think not go in more details. Okay, but anyhow, because we are going to give another version of derivation, so you must keep in your mind what is derivation. Okay, so derivation means that is the additive map is satisfy Leibniz rule. Okay, so that is mentioned in the definition. Okay, and then this is the example we gave you time to time, and somebody are interested, just verify a little bit mathematical check. Okay, are they satisfy these conditions, or it has, so means if you have any doubt, then we are with you at least more than 1.5 hours, you can make chance to make things clear. Yeah. Since we are talking about the symmetry by derivation, so let me come on what meaning of what means of by derivation. So that means we have a map, additive map from R cross R, from R cross R to R. Then if you look at this, the additive in the first argument, okay, so you look like that, and then D is additive in second argument. That means D is additive in both argument, okay, and then this is such map by additive. And what is the meaning of the symmetry and what is the role of the symmetry? So the next definition is like that. Symmetry means you look like this dx by, so that means if you change the role of x and y and relation does not change its value. Okay, so you can work means with x or y, but it does not change anything. So this is makes symmetry.
This by additive mapping was something like by linear.
If we have algebra, then definitely we call it linear. Okay, because just we have talking about ring, that means we just delete the term linear. So we don't need linearity when we have x. However, if we are talking about algebra, then definitely it is bilinear, means linear in both arms. Okay. Yeah. So, and let R be a ring, then the mapping of this, I just need to give some basic examples to make convince more interesting. Because we are talking the bi-identity map, symmetry mapping. So these are examples you can check easily. This is x plus y. This is not complete. So this is dx plus y, x plus y. So we call our symmetric map. Of course, you could change it value, because we are talking the ring is additive subgroup. So we always write x plus y is equal to y plus x. So definitely d of x y is same as d of y x. Then next one is dx y is equal to x into y. So definitely is it work as previous? Answer is no. Why? Because x y cannot write by x. X into y, you cannot commute with y into x unless otherwise r is commutative. So I give you both examples. Okay, symmetry and non-symmetry mapping. And then we define this symmetric by mapping. D from R is called symmetric by additive if it is additive in by additive and symmetric. Symmetric by additive is additive as well as symmetric. Okay. Another term we using is trace. So what is trace? it has, look at trace of symmetric biology map D from R to R defined by the XY by distances. X. So our course, we need to check it is. At biology, it is symmetric, of course symmetric because here we have X equal to Y. So this is same. Now look at here. If you have, it is obvious, if you have map, it's symmetric mapping, which is also biologic, then the D, that is the trace of D satisfy this relation. This is very important relation because we use this relation time to time without mentioning. To keep to remember this relation when you have this map R, then you always write X plus Y. Okay. Yes, and then this is beautiful example for making the subject more interesting. Okay, so let R be a ring of integers, most popular ring. Okay, and then this is R. Means we construct R over Z. Of course, then this is what is non-commutative ring. And if it is non-commutative, take this denote A, K of this type. Okay, XK of this type, and it is define D from R cross R. And then you will check D is this and with small d of this type. And then check this is what we have taken above, then it is easy to see D is trace of D. Of course, this is, look, this makes sense is because non-linearity, and this is also accentuated. So when you're dealing with the multiplication of two matrices, and you will find such interesting example. So the idea of symmetric derivation came after the work of USIIMathCorner, who did very fundamental and scholastic result that was published in the year 1957. And this paper was the first pioneer paper in this direction, because before there is no work with derivation on algebras. And even then, if you look on this paper, portion of this paper, there is no reference. You very rare such papers is possible without a reference. That means if paper does not have any reference, so this shows two things. Either this is exactly the new work and the new idea, okay, because there is no anything available in the literature. So that means the person has fun in mathematics. I think he himself does not know why he is doing such and such. I'm telling you, because he has only one paper in derivation, no other. Okay, so I think he sometime maybe sitting alone with coffee, okay, and he doing mathematics, and the idea came in mind. How this might look like when we connect with certain class of things. Okay, so many times I quote one example for researchers, because I was I was in USA. So one of my friends, Sergio and some other, we are sitting together. Then they joke. So we offer a coffee. Then somebody took one coffee equivalent to write one research paper. So means one coffee equivalent to one research paper. So if anybody wishes to coffee, then he must have agreement to write one research paper. Okay, so this time we are talking. So he is such that he has coffee in hand and sit alone, and then he write down the whole paper by bed. It's first, but he make connection with prime rings with derivations. It's very important because the commutativity at that time, I think on the top, because there is a lot of work going on based on commutativity of polynomials during 50s and 60s. Okay, so maybe the idea his mind is let me check what is the relation of derivation to the triangle. So this is the output of 1 cup of coffee in terms of one research paper. And now this idea gives several new directions. I talked in before some lectures. It plays a very important role, not only in algebra, in analysis, in coding theory. And there are a lot of good application of derivation in coding theory. I remember when I gave a talk in Bandu last year, then I gave several application of derivation in area of coding theory, apart from other algebra forms. So this means a very important topic for research, has means good applications in algebra, in font science, and in what we call function analysis. Okay, and for function analysis, just to put on Google that derivations in C-star derivation C-star algebra or Banach algebra, you will get very good results. Anyway, so the idea of derivation in race was given by Jacobson in his classical book. Okay, it's not new, but the things are generated by the work of E.C. Posner in the year after the year 1956. And then there are several development in the field, and this development in kind of the bioderivations that they are going to define is due to a guy, this is called Muska, I think he's Hungarian mathematician, G. Muska, and introduced the concept of, if you look on the glassing method in 1980 and then 1987. So this is the time when the symmetricity and the idea of phi derivation came into the existence. And then I told you it has various applications in functionality. So this idea was not in the context of algebra, but in the setting of functionalities. That is, if you look over there, last one, he gave the representation theorem in the inverted space. Okay, so he had some type of idea about why to make the inverted space. But after that, there are several researchers who are already working in functional analysis. They are check these notions in the setting of race and algebras. So in the first, let me give the precise definition, and then we come on its side. Extension and other. Yeah, look at the definition. Very carefully, because we talk based on this, I think may just note some here. We will make many things we do around this definition. So, yeah. So semantic biology we have already defined. Okay, the semantic biology meant D from R to R, the R is anything. Anything here means we are talking the and adjectives. Okay, that keep your mind. We are talking for algebra and we are talking adjectives. Then look at here, the semantic biderivation of R. If it is a derivation in each argument, means derivation is first argument and derivation is the second argument as well. Okay, so and what does it mean? That means look over here. This is derivation of first argument, then the derivation of the second argument. So if that means we have argument and it is the derivation of first argument as well as the second argument, we call it semantic biderivation. Okay, semantic biderivation. So look at interesting.
You said that for every x in R, the match y from y to d.
Y is an X. This is mapped by X to Y, right? X to dx by, because first we are already on X, okay? First component. So here is X. Then after that second component, Y. Because we have symmetry, so this makes same change. But this is between X goes to dx by and Y goes to this type of map. Okay, that we need. And then, so these are some interesting examples, and let us check what connection between derivation and biderivation. So I asked this question to you guys, if you really understand, somebody want to understand. Okay, so this is to students, make connection with derivation and biderivation. So how make connection? Means what is the relation between derivation and biderivation? Now more specify, are derivations or biderivations? This is question. Yes? Are derivations or biderivation? What is the answer? Please. Yeah? Because otherwise, if you not understand, then that means there is need to go about it. I want to be very sure you understand the relation between derivation and biderivation. Then you will be that. So simple question, what is the relation? I again ask, every derivation is biderivation or every biderivation is derivation?
Derivation. I just guess that a derivation is the by derivation and the trivial way.
Every
Derivation is by special case.
yes, I think it shouldn't be involved. Otherwise, you should understand, because I already defined the derivation and then come on biderivation. Anyway, but if you want to understand, you must be enjoy. Otherwise, you will not enjoy the lecture. Okay, derivation and relation between derivation and biderivation, because every y derivation is a derivation. However, the converse need not be true in general, because derivation can not be biderivation, because derivation is just derivation one argument. But for biderivation, we need two arguments. That means map from R class R class. So keep remember. So because y derivation is of course derivation in one argument. So exactly there is no relation, but if you think on you fix that first second argument, then it's a derivation. Okay, so this is connection in y derivations may be derivation, but derivation cannot be y derivation. So these are the examples which make clear. Okay, so the example of bioderivation which are not derivation. So I ask, please check. Please check quickly. This is an example of bioderivation which are not derivation. Okay, either check first or the second step we do. But this is what. Look at the first. Here what we do. We are these derivation. Okay, R is commutatively and define this capital T as. Which capital D means this is the derivation over R. This is also derivation over R. So this is multiplication of two derivation is by derivation. Why? If you take on first argument x1, then replace x1 by xy and check property. For the second argument, you replace this x2y again x2 by and check. So then it is of course by derivation. By identity, by derivation, okay, which is not derivation, and easy to check. Okay, then the second is for any by derivation D. This is by derivation, that means derivation in both are. We define another D from R to R in that way, that means the second argument will take to 0, and easy to see D is our derivation. So I try to make the second argument is 0. Okay, and then it looks like this might look like a derivation. Okay, because we reduce it from second argument is 0. Okay, and then it has derivation. Otherwise, this. So it is interesting to see additive converting where they have very close means the theory of derivations has created a very beautiful theory that is called theory of commuting and centralizing matrix, or in general theory of functional analysis. Functional identities. Okay. So the most important contribution of theory of derivation is to give a tool that is called functional identities by Beta, Bracer, and Martin. All three are, the generation of, we call Husky, because Veda is student of Husky, Matthew Bracer is student of Bookman, and Martin is also had connection with the colleague of Husky. So they all three make a theory that is called theory of functional identity. Maybe you can click on Google, and this theory is due to the notion of derivation in rings and the theorem by Kost second, because he called if D is derivation and satisfies the condition. Like if you have any map, you have R as the ring, and if you have D from R to R and defined as this belongs to ZR. For all X belongs to R, then we call this is centralizing derivation or centralizing matrix. Centralizing matrix or centralizing derivation. And we call something if this is equal to 0 for R, then we call commutative matrix. So if you look one of the main contribution of theory of derivations in ring are these maps. Because the first map, if you look on the first result of Kost proof, if they satisfy this condition, when R is prime, R is prime ring. What does it mean? That is A R B is 0 implies A is 0 or B is 0. So if I have such type of ring, okay, and satisfy this condition, then this R becomes commutative. R becomes commutative ring. So this was the first called Postner's second relation. And this result introduced the idea of these matrices. Later on, people did call it centralizing or commutative map, and these maps give the idea of theory of functional identities. Functional identity, very famous. If you put just on Google, you will find out. Let me check. So this was the most important and contribution of derivation in algebra. Okay, and why it is most important? Because it solved 100-year open problem by Haskell. And what is problem? Problem was this, just like you with the idea. If you have a man, okay, from leaving, okay, then this how to characterize these men means you characterize the Lee and Jordan ideas. Lee man is already have the idea how to satisfy this condition. And X is 0. If R has leading, so they has some new type of this. So this powerful tool solve this problem in 3 papers that called Lee map conjecture. So very famous in the algebra. If you put on Google, you can just see very famous conjecture. So this is was the most important contribution of derivation in Lee algebra, where we describe the Lee maps, characterize the Lee maps, okay, by this theory called functional identities. And now, then we will have different other areas. So come on back on this topic. This is bi-derivation. So in the similar line, people are thinking about how the behavior of bi-derivations on certain class of rings building. Okay, so let me move forward.
The definition of the bracket X is the last one. Yes.
This is map, one type of map. Okay, so we define in such way. No, I think this is like this. Good. This is like this. And F means we are talking by a map, by then fix and alpha. Okay, like this, by like this. Okay, it must be 2 arguments, so that is not one time. So then the map of this type and this card, they look like a bi-derivation. Okay. So the study of symmetric bi-derivation are rings upon the rings interpretation and general architecture and the aesthetic maps. So basically there are two, we are talking about 2 type problem. What by using the derivation of rings, if we fix the structure, okay, if we fix the structure, like if we like R prime or same prime, then we describe in a map involved in the function. Second thing, if we fix these map like this derivation, R by derivation, then we describe the structure of rings. Means what type of rings is commutative, non-commutative, or so this is the 2 point. So means when we have a derivation satisfies certain identities, then either we classify the rings or we characterize the identity maps involved in the functional identity. Like if you look over here, this is the one type of functional identities. So if we fix this D, like the derivation, okay, and R is prime, then we find out this R is commutative. If R is commutative, this derivation, then we find out this means if D is R is non-commutative and D derivation, then definitely from here we conclude D is 0. That is famous result of Kost. So means to know how to solve these functional identities. Okay.
And question.
Yeah.
In your previous slide, maybe less than and then you give like a small e. This one, yeah. Before small d applied to x is equal to small big D. I think max record or before.
There's no D here.
No.
This one, now, the next.
Yeah, you have.
After this.
After this.
Okay.
Yeah, this one. Fact. Yes, it's a B derivation and then is a small d, yeah, small d applied to D.
You are just starting here.
Any derivation, oh yeah. Okay.
In fact, mathematics are things you can control when you have pen or paper. You cannot control by just talking. Okay, so that makes confusion. So now I make more clear. No, I understand. This is what we're talking sometimes now. So that's why when you deal with mathematics, then you must have a pen and paper. Otherwise, you cannot enjoy with mathematics. Okay. So this meaning of this mathematics is this. This is the meaning. Okay, so that is the capital D is biidentical map with this form. Now our claim is it is semantic biology. That means you can satisfy it is identity with both argument. Now you can check yourself. You can check because they are identified. Argument is first you check it is identity. With respect to x1, that means you replace x1 by y1 and check. This means if you replace the x1 y1, then you have the x1 y1 the x2. Now because D is identity, yes. D is identity, so we are going to write x1 and D x2. Okay, go ahead. D of x1, D of x2, then D of y1, D of x.
Derivation is like arbitrary operation.
Yeah.
But at least it's possible to like generalize into like n derivation.
Let us have Norman. We have this part also because we start from in one argument, then two argument, then go for n argument. So that means you can check each and if it is like this, then you can check the the derivation is also both argument. That means if you replace x1 y1 and verify this is derivation. Okay. Okay. So sorry, I already applied the next step. What is the next step? I think what is the next step? So we call it internal. This is what the look at the definition. X1, X2, and plus sorry, D of
Y1.
X2. So that's why it says the so that is D is identity in first argument. In similar way, you can check D is identity in second argument, and then you have to verify it. It is also derivation of both argument. That means you will also check if you replace this x1 y x1 y1, and then you will find out x1 y1 x2 is equal to What is d of x1, x2y, and x1 d and y1 by check this. Okay, then again you replace next part for similar calculation for x2. So it may be derivation. Okay, and now clear? Good. And similarly, if you ask, then ask you to change this one also the same way. Okay. Then yeah. So this is what we try to construct by derivation, symmetric by derivation. Okay. So I'm already sometimes talking in math, when talking in mathematics. In this theory or matrix is very important when okay, later on we will take these portions. We have some portions. So yeah, so look at with the help of this matrix, we find example in non-commutative rings. Previously it was arbitrary in case of commutative or non-commutative rings, and this is specifically in the setting of non-commutative rings. Okay, so this is the derivation on non-commutative. Okay, so again the matrix has the same meaning. Okay, the biologic, so we take some element from here and some element from here, and then we operate. That means this capital D of this complex. Okay, and what happened? No, sorry. So let me come on to check the involvement of the matrix in setting class of rings. How we had in some special kind of rings. So in the year 1989, Bookman had generalized the very classical and classical result. I'm talking about the first result of Kost, that is these commutative. And this non-zero, then R is commutative in case of prime ring. So Bookman is one of the founding members of this area, has done tremendous work in the field of derivations, not only as a functions, lot of good things, yes. And then look at it, let R be non-commutative prime ring of characteristic not true. Characteristic not true means 2x is equal to 0 implies x is equal to. Sorry, 2x is equal to 0 implies x is equal to minus x. Okay? So this is meaning of characteristic. So in case of that, this symmetric by derivation with trace D. Okay? Suppose D is centrality. What is D? D trace associated with capital D. Okay? So this then if this trace is centrality, in that case D becomes 0. On the other hand, as I told you, if you fix this R, like if you just take R any primary, okay, and this is non-zero, then what happens? Then R becomes a commutative. That means primary with non-zero trace is implies R is commutative. Okay, this is parallel to the result just mentioned by Osner, that is if D is the non-zero derivation which is commuting, and if R is prime, then R is commutative. Okay. Yeah. So then we involve some more type of things. Another result in the same direction, R is prime ring of characteristic not 2, D1, D2 are non-zero derivations of R. Then, with the help of these derivations, we construct another bi-derivation. Okay, this type of map. Okay, this kind of map है वो derivation नहीं होगा. This cannot be derivation. However, it is a bi-derivation. Okay. So, if you look on this result, the target prime ring, then D1 is this type and D2 from both are symmetric. And with this condition, then there is a symmetric biodirectional map B from R to R with this condition. Okay, but D1 and D2 are trace of D, capital D, and capital D1. And where this especially an activities of B, then if this happens, okay, then either D1 is 0 or D2 is 0. That means there's no non-zero symmetric bi-derivation on prime ring of characteristic different from 2. Okay, there's some other, but we now move on some other type of things. Then people are trying to study the results on some well-behaved surface of the ring, like ideas, Lie ideas, generalized data ideas, and so on and so forth. Then now I think we move on. So this problem is still open problem because in for wider class of rings, this converted this later non-competitive triangle are different from 2 from R to R, and then different from 2 and 3 also, and the symmetric by derivation and stress and is greater than equal to 2, and then this this relation holds, and still we hope and believe D is 0, but in general setting the result is still open, not we are spoken about. Okay, then now so in the year 1993, the Bracer characterized by derivation in more general setting, and he proved every by derivation are non-commutative primary. That means you have a class of non-commutative primaries. Okay, so his claim is not his claim, but his proof. He proved every by derivation on prime ring, a non-commutative prime ring is of this form: d of x by lambda times x. What is lambda in C? Here C means the centroid of prime ring. Centroid means if we have a the extension ring, and then this extension ring is sometimes prime, then center becomes a field. So that means lambda is from field. Okay, so this type of every by derivation is it has this one. This is very important result because it's characterized the whole things how by derivation look like on prime non-commutative primes. So this is one of the wonderful means path results. He characterized all by derivations on non-commutative prime has this. C means extended centroid of R. Extended centroid of, yes. And then in the same paper, he gives another type of characterization, like if you have this by derivation non-commutative, and then again he say he in more general setting instead of rings, he just the ideas sometimes, okay, and then QR modern ring of symmetry. So we take R B from here to here, and R non-commutative. Then again find out these maps. Now I move on another type of. Okay. So this is we are going to make more extension. So first extension is in terms of the semantic alpha biodivision. So let alpha be a name, let R be a name, alpha be an automatic marker. A semantic biodivision mapping the from class R is called semantic by alpha. If you look over here, okay, that means this term is same. However, here we impose alpha, where alpha is any automorphism or any identity map. Here we take automorphism, but even you take a definition does not require the automorphism, you just take endomorphism. And then if this is for first argument, similar result hold for the second argument. Okay, so if you take alpha and identity map, then you will get the notion of biodivision. Okay, so this is one type of extended version of symmetric biodivisions. This is example. Okay, so for quick you can write down then check later on. Because I move some more then of course the people will take similar type of questions work and document results on taking symmetric alpha derivation, study similar problems. Again, Bracer, another paper described structures of bioderivative, alpha bioderivations. Okay, so just I mentioned. Look at here. Data will not be primary alpha be an automorphism of R. Now here alpha is automorphism. That's clear because here we use the property of alpha. However, in definition, need not be take alpha automorphism. You just take any one. Okay, but here important because we using its properties. So look at here. Then this D from R to non-zero alpha biodivision, and then alpha is X inner. There is what that my X inner. So look at here. That is there exists an invertible limit B in the symmetric ring of quotient. Okay, with this condition. So alpha X is equal to B X B inverse. With this property, and we take D of this form, D of X y equal to B times X y. So he described the behavior of this map in terms of this alpha automorphism. And also the same guy has a lot of good things in other countries. So the next question, if you compare the result by map G from R to R is called generalized by. So we are going to the more generalized version. Okay, so generalized by derivation. So the definition is same as G from by if for every X Y G X Y. Okay, and Y X Y R Y X Y remaining is same as in case of D. Okay, and the key result is let I be a non-zero ideal of primary R. And G from I equal to R is generalized by derivation. Then there exists an element in symmetric decomposition. Then this G look like this. So it's very beautiful characterization of by derivation in terms of primary. Okay, this one. So, if you look on connection between generalized biodivision and biodivision, of course, every derivation is a biodivision because just you take G same as D. Okay. However, the reverse implication does not hold still. So that means there exists generalized biodivision which are not a derivation. by derivation. So this is what you can quote this example. Okay, this is generalized by derivation, which is not by derivation. You check yourself if somebody is interested in that. Okay, and there is some other important observation. Data are non-commutative and free from I class R to I is ideal. I is ideal. Okay, then G is symmetric, that means we satisfy this condition. If G is symmetric, then every G means every generalized by derivation has this representation. Okay, moreover, if G is anti-symmetric means like we say symmetric D of x y is equal to D of y comma x. When you tell anti-symmetric, that means D of x y is to minus D of y. Okay, this is in meaning. So that will be anti-symmetric, and then this G x y has this form. So in different settings, he classifying these maps in non-commutative prime. And then in the year 2011, with my PhD students, I extended this idea in more general setting, and we introduced, in fact, integration in derivation. So I defined some new type of terms. These are known as the first one is star by multiplier. In fact, and star by generalized star by derivation. Multiplier we not define, so that we define first what is multiplier. So if you have map D from R to R with this property, D of x by x for R x by belongs to R. This notion is known as in the literature left centralizers or left multipliers. And if T is equal to x T y, this is called right centralizer or right multipliers. If T is both, that is left and right, then we call it multiplier. Okay. Now, if you have like x from R cross R to R with the condition x of x by z is equal to x z y, and this gives me name left by multiply. Similarly, we define right by multiply. Anyway, and so this is called multiplier. Okay, and similarly we define right multiplier, and it has these notions. Make algebra very interesting. That this gives the make a bridge between algebra and analysis, because these notions in fact is studied in function analysis. So what algebra is to combine these notions and study the behavior of these in algebraic point of view. So its behavior is very important. Like one next slide, you will carefully check, because most of the example for this type of map is that is T of x is equal to lambda x, and T of like x is equal to this is this guy, because if lambda if you're commutative then this is both for left and right multipliers. So this when lambda is a fixed element, lambda is a fixed element. So every map of this type is called left multiplier. So if you look on previous slide, then the combined notion of left and right multipliers, and if you write down here, multiply, so here lambda times the multiply like that. So these are very, very common and famous example of left multiply or by left multiply in functional analysis. So we define these notions here. That means a symmetric biology map and from R to R is said to be a symmetric left star biology. Star is inversion. Star is in that we use and we introduce another map, in fact. Okay, and map is if you have a star, this is map from R to R. Up to this is additive. This is additive. This is additive. And satisfying condition x by star is equal to star, and then second, that is x star of star is equal to x. This is for all x and y belong to R. So this is the map which satisfies these conditions. Additive map, then we call inversion. So that means we introduce this new map here. Okay, so and the link with this map is called star ring or links with inversion. So we use this idea here, that is M x y z is equal to x M x z by star. So we call it symmetric left star y. And similarly, right symmetric right star y. If M is both left as well as right, then we call symmetric star y. So, and then we define the another notion that called symmetric generalized star bi-derivation. And if you look to the distribution, if there exists a symmetric bi-derivation, okay, that means gx by this gx by star, and this is what? This is the bi-derivation. So in fact, if you look at the connection between bi-derivation and generalized bi-derivation, every bi-derivation is generalized bi-derivation when we have P0. Okay, and again, the converse need not be true. That means there exists generalized bi-derivations which are not bi-derivations. So in that context, if you look here B0, so if you look over B0, then this becomes a bi-multiply like this form. If we have ring with involution, that means in case of ring involution, we write like that. The x by x z by star. So this is what we call left by multiply. Okay, we call by multiply. So here we combine these two notions. That means left by by derivation and left by multiply. And the first result in this direction is in case of R is we are saying prime star ring, and if I am from R to R square remain with this condition, that means N is by multiply. Then I am max R plus R into ZR. That means I am the range of I am is go in the center of rings. Similarly, this is the second factorization. If R is semi-prime star ring, semi-prime ring are ring which has no non-zero nilpotent ideals. On the other hand, if you have like in case of prime ring, we already defined this type of ring, like here. So here, if A or A is 0, implies A is 0. Such ring we call semi-prime. This is equivalent definition in terms of. So if you start semi-prime star ring and R and symmetry generalized by derivation B with associated non-zero symmetric by derivation B, then G makes R into ZR. So when it is that is simply map to the center. So that is it may be connection with the central map. Is generalized by derivation has connection with the central and maps in general. And then look at the new type of definition. By map is called left and right. In fact, okay. So the left by derivation are Jordan left by derivation if this condition is satisfied. In fact, the idea of left and right derivation are important in non-commutative. Otherwise, it does not make sense. We are commutative, then you can manipulate and we get the same thing. Similarly, in the same paper, we introduce new idea here about generalized by derivation. And we characterize all these maps and find very good information about these maps, how these maps are look like in case of prime or semi-prime rings. But I move the another type of things, so I will just bite and go. Yeah. How much time? Give me. Yeah. So, we move on. New type of sigma tau by that's map associated with two more maps involved in the definition. So let sigma and tau be automatic on R symmetric by map B from R plus R is called symmetric sigma tau by derivation if B x by is sigma here and tau here. So, if you take tau is identity map, then they get the idea of sigma by derivation. Okay? If you take both sigma and tau are identity map, then you will get idea of by derivative, I by derivative. I think I know this charge in chart. Okay, sorry. So this is what we call symmetric sigma by derivation. If this is derivation, when sigma derivation is first argument and tau derivation is second argument. Okay, this is the meaning of that. Okay, so and then we define more symmetric generalized sigma tau by derivation. The idea is, these are notions extended the previous notions. When you have sigma and tau are identity maps. Okay, and moreover, if the associated by derivation is 0, then becomes by alpha by multiplier as sigma by multipliers. So look at behavior. This the code is first result. Let R be prime ring such that characteristic of R is not equal to 2, sigma tau be automorphism of R, and U be non-central square closed DI. So I think this is maybe new for someone, so let me explain. So the idea means U is active subgroup of R and closed with this product. This product we always mean Lie product, that is x y minus y x. So this is in terms of commutator. So Lie ideal means additive subgroup and satisfy the condition U are in U. Okay, so that means U is closed under Lie product. Similarly, if the Jordan ideal, then it is closed under Jordan product, that means the function denoted by x. So there are every ideal, left ideal are, the examples of Lie ideals. However, there exists a Lie ideal which are not ideals. Okay, so this result will be proved for non-central square closed Lie ideal. So ideal with the condition, if U belongs to U implies U square also belongs to U, we call such ideal and square closed Lie ideal. So in the case of Lie ideal, the symmetric generalized sigma tau by derivation with a static symmetric sigma tau by derivation from R to R, with this condition, okay, then G is left, sigma left by multiplier. Okay, that means we characterize generalized sigma tau by derivation in terms of left multiplier. That's every sigma tau by derivation on prime Aligargh is different from 2 is sigma left by multiplier. And then we have another idea of class type that is called V generalized sigma by derivation. So they are an acceptable algebra or acceptable, and G from Martin quotient, and this is biodiametric alpha beta are automorphism. Then the mapping delta from R to R is said to be V generalized alpha beta derivation associated with the term V as already came from this superlative, and alpha beta are automorphisms, and then D is biodiametric map. So this combination and satisfy, look at here, if A x y and z is equal to this form, okay, and because we are dealing with symmetricity, then you have also the derivation in first argument, means generalized alpha derivation in first argument, and generalized alpha derivation in second argument as well. And then we classify and these maps and describe the sector of these maps with the help of this result. But this is by Philippis and Bejo in the year 2022. I think let us move more because, So look at the recent work in this direction by Parveen. This was in the year, 2022. Basically, this result is related to this series of two symmetric derivation. Okay, the result is look like that. Let D1 and D2 be two non-symmetric derivation of a ring R with trace D1 and D2 with this condition. That means, and think about the multiplication of two derivation, need not be derivation. Same as composition of two maps need not be a function of composition of two map need not be a map. So here D1, D2, the range of D1, D2 is where in prime matrix. Okay, and then for me the characteristic of this quotient ring is not 3. Then if this happens, then the range of R under D in R are D2 R in P. So that means the range of both of these map in prime matrix. So this result in testing from the other setting a point of view, and then they also look DB symmetric by division or reward with test D, and with the same private idea, the characteristic of P is not 2 and D is on 2, a D to the power R. Okay, D to the power. This is in fact look like the nilpotent of derivation, power of derivations. So D, if I only dp in P for any positive integer. This is in fact very good results and give some more excitement. Okay, then they move for try. So look at it. From Y we are moving from try. Okay, so I skip, then we move for I. Okay, because the idea is same. From one component we move two components, then three components. So Y try, then we move for n component, and we call n. Okay, so I think it will not go in more depth. Yes. Okay, we will reach on here. This is what your question about about 79 type of method. Okay, so here is the this n is greater than equal to 2. We fix integer and Rn we are already know of this form, and then we take off D from Rn to R. Okay, so now we take n components in place of two components. In place of y, we take then n equal to 2 is y derivation, n equal to 3 try derivation, n equal to n is we call n derivation. Okay, so look the domain that is Rn. Okay, then D from Rn to R is symmetric permitting. Now we put find the n derivation we need the symmetricity of n components. So for the symmetricity, it's said to symmetric permitting symmetric, we have the other permitting. If dx1 comma to xn is same as d sigma 1, sigma 2, sigma n for all permutation sigma belongs to Sn. As yeah, symmetric group of order. Okay, so this more environments. Okay, so now and additive, that means additive is E argument. First argument, second argument, third argument, then n argument. Okay, so we call that is additive in E slot means each argument. The map D from Rn is set from Rn to R is set to be symmetric and derivation if D is symmetric. Okay, and satisfy. Look at here, x1, x2, then we take I place xi and xi prime. So we are talking about, you say, an I place. Similarly, then take this element here. Okay, and now look the division what happened. Same as only if you look on here, this part is your xi prime. Okay, and then here is plus. Here is plus because we are talking the derivation. Okay, so plus xi and xi this. So far, n is equal to 2. You have by derivation just discuss. So the idea of symmetric and derivation cover all the previous idea, and it's biderivation, triderivation, and so on and so forth. So then, definitely because when we're talking about the biderivation, there must be a stress. So trace for analytic map D is defined by A. So if you remember, when we talk for by n equal to 2, just we take up to here. Okay? So now we extend it. And that is called trace. So if D from R to R is symmetric and analytic, then the trace D of satisfied acceleration. Maybe you remember when we call n equal to 2, then dx by plus dx plus dy plus 2 times dx by. So here this term, if you run and check, you will get all these things. Okay, but it's little how the complicated we are dealing with summation. Okay, but very interesting. So clearly, n equal to 1 derivation is just a derivation, n equal to 2 is symmetric by derivation, n equal to 3 is symmetric 3 derivation and tri-derivation, so on and so forth. Okay, and then look at the example. This example is more than a year to construct because it's stating is very important. When we put something here, is fail. When here, again fail. So it will take a lot of time to construct example, stating where we have to put elements. Anyway, but success finally. So see the complexity. Interesting question. Why we take complexity? Okay, and this is non-commutatively, and then if you remember, we have to take same example of this type. Okay, the only difference in biderivation, the only difference is here where in the biderivation just we take 0, x1, x2, and then below 0. Here we take x1, x2, xn. So if you fix n, you will get example for biderivation, example for triderivation, and what type you need, you can just fix n and find out according to your needs. Okay, and then this D is permitting analytic map, moreover, D is permitting and derivation. So this is the best example for permitting asymmetric and derivations in this. So by definition, it is clear that permitting and derivation on a ring is and derivation on a ring, but reverse cannot be worked. Okay. So for this, if somebody identifies, this is more natural. Another example. Okay. So how these things are not same. So this is the counter example. We try to find out. Okay. So that. So result related to these maps has long history. We are not going more detail because we are going to make connection of these ideas with our own works. Okay, and then we will give you some the open columns based on the recent works. So we're not going more but there are so many things here. And then our colleague, our Aligargh group, also has beautiful results in this area. Yeah. And then we leave again some. Similar as and generalized and derivation, we define generalized and derivation. Okay, means we follow the same idea of and derivation and then generalized by derivation, and we extend it for generalized and derivation. So just for generalized, nothing to do, just we involve both derivation, means generalized derivation, and another matrix. Okay, so and greater than 1 is positive integer, permitting and analytic map. This is still sigma from Rn to R is known as permitted generalized and derivation if there exists a permitted line derivation just defined before. And combine this idea of tail, but this here is this sigma, here is this. So in terms of both, that means if you every and derivation is generalized and derivation, but again the reverse implication does not hold. Are you agree? How we say every and derivation is generalized derivation? Anybody quickly answer? Because this is not a big problem, this is just big generalization. So I think we must be think out how these notions are. I always say every derivation is generalized derivation. In the same time, I'm talking every and derivation is generalized and derivative. So quick answer. How?
We take the delta is equal to sigma.
Yeah, sorry, you're right. Because this is just identity map. Okay, so after this is also identity. This is also identity. So if you take this sigma to be this, is what that is in case of generalized, A is any identity map, D is the derivation as stated. So if you take this A is D just A, the identity map is the best. In the same sense, if you take this is equal to this, then you have and derivation. That's why I am saying every and derivation is generalized and however the reverse does not pass. That means we need a generalized and derivation which is not a and derivation. That makes sense to study the behavior of generalized and derivation. Okay? So this is the example. Again. Okay, so this is the example, and this R and there is sigma considered like this. Sigma is this, and where is yeah? Look at here. This is component by perhaps this we must, because we have Rn, so we multiply. Then we have A1 in An, and then this is C1 The sigma is permitted generalized and derivation on R as written and derivation. And which is additive and derivation? Just like before. First example. And then combine all these issues. There. Okay. So then motivated by the idea of generalized derivations. Our colleague Ashraf and our another students combine this idea and study some problem for generalized and derivation instead of generalized derivation. Okay. So the result is here and is between two prefixed positive integer R and R primary. Suppose omega 1, omega 2 are trace of permitted generalized and derivations sigma 1, sigma 2, and with the condition delta 1 is non-zero, then the trace. And if this happens, means ignore omega 1, they are coming, then there is lambda and the extended centroid of this field, okay, with this condition. That means delta 2 is linearly dependent. So that means they are linearly dependent. This is another characterization of these maps. And this is another result now moving to whenever we have the idea about generalized derivation and derivation, then we must have associated idea of multipliers, because generalized derivation is the idea which combine the multiplicative maps with other maps. Okay, so that makes sense. When we have generalized and derivation, then we must have and multipliers. That means the associative and derivation suppose 0, then we will get and multipliers. So we symmetric and multipliers, so we call permutive and multipliers. So this is what is the definition. I think it's very not complicated. Okay, this is here to look over, and then this is just multiply on your side. Similarly, if you have right multiplier, then multiply from the right side. So that means we have the idea of and multipliers means left multiplier and right multipliers. Okay, so and then these are examples for left and right multipliers, and this go somebody in thesis, please go ahead and check. All these just given, I give you a link of my discussion, so where from where you can find paper or something like that. Okay, then I leave, then come on the and more general idea. And more component like SQ and derivation. That means ion derivation achieved with another line. Okay, so that is the additive map and additive map from Rn to Rn, and alpha is the automorphism. Then if you just look at here the definition here, that is this same as alpha xi. So in fact, if you take alpha the identity map, then you will get idea of ion derivations. Okay, so it's just the narration. This example are not so detailed, and because I just click and move on the next part of my discussion. Okay, how much time is left? Something left for discussion also. I think you move. Try to conclude, otherwise. So recently, this year, we again introduce these idea of and derivation, general and derivation. We study these results to rings with enumeration. So this was the first, see the definition, then the first result. I appeared recently in the last month. So with my student Bapak, additive made this with this, and we introduce rings with enumeration. Okay, so here in place of the map we fix, means in place of sigma we take enumeration. Okay, so the idea is that if you look over here, then we have this x prime. This is enumeration. So we call semantic and star derivation. Okay, and if you concern for the examples, these example is here. That is C beginning of complex enumeration, and this is what we define enumeration as C, where Z bar denote the complex conjugate. Okay, and D from this to this of this type. This is lambda time Z1 minus Z1 bar and Z2 minus Z2 bar, so on. So when lambda any fixed complex number, then this D is and star and derivation on C. Star and derivation on C. And then our algebra group in the year 2015 find this particular type of idea. That we star ring, if I do this non-zero and derivation, then of course R is commutative. So parallel result to the positional one in end. Our second one, let R be 2003 prime star ring. First star derivation D1 and D2 with this condition. Okay, and then we say either D1 is 0 or D2 is 0 if D1 time, if you know, commute this map with this definition is 0, then this gives or one of them must be 0. And then we introduce the idea of this is we call alpha beta and derivation. And also we will not go in more detail, but we have very good examples of these maps. Okay. Okay, and yes. So this is the recent work with my student. Okay, that is let n be greater to fixed integer, R be also free semi-prime ring, and W is non-zero ideal of R. If R admits to non-zero symmetric and derivation, that is two symmetric and derivations, and satisfying this condition. D of x, y, and x dy then R had non-zero centrality idea. The motivation behind to this result is very classical result by Bracer and Martin. And the result was published in 1993, Journal of Algebra, and that was he described dxy and x d g y that is 0, then they conclude this either R is commutative or D is equal to G. This result, in fact, he proved in that paper. And so motivates the idea from this result. Recently, we choose the identity dx, okay, and y with this small d and small g are traces of this d and this g. Okay, then R had non-zero central idea. This was the first result of this paper. And second result is this, maybe for symmetric and derivation, let R be entire simplification time ring, and done to be non-zero ideal of R, q greater than 1 is integer. So d1, d2, dn, they are, the q derivation are Rn, and this condition d1, i1, d2, I plus, they are 0, okay, where di's are trace of di's, then one of the following holds. What? Either di varies on I1, d1 varies on I1 first component, or all dpx as a left multipliers. That means all this what we call derivations, and derivations, they are look like as a left multipliers. Okay, left and multipliers. Okay, so that is the first result of this. Second result of the paper just we mentioned, and then this is the another paper. Okay, we using the similar idea and try to find out some more interesting result by considering just behavior of these maps in prime matrix. How the action of these maps for the prime matrix. So we have this and derivation, okay, and then if you have symmetric and derivation, with and this is a trace which satisfy dr is y in p. If you remember, the result of Kost, what that one? That one is belongs to ZR. We start our discussion from this result. Okay. So then what we say, if R is prime, then R is commutative. Okay, this is what the question for theorem. So basically this result for and derivation, however, we describe, that means we not do the same things what Kost has done. We find out the behavior of D, how D look like, and the structure of the quotient ring by its prime idea. So this we are then one, if D is, that will the trace is commuting on P instead of Z, here is center of R. So in center of R just we take prime idea. So it's and that form, and then we see the range of the dr in P R upon P is a commutative integral domain. That means the quotient ring associated with this ring is commutative. So we describe the structure of the quotient ring via and derivations. So these are the some problems based on these last two papers. Okay, understand one, they are appeared in 2023. The first one is we take R29 symmetric and derivations D and G, and with traces D and G. If we say what happens if this identity holds in P, then what can we say about the structure of D, G, and ring itself? So if you remember, we told you two things. If we fix the structure, then we describe the maps. Okay, we describe the structure of map. If we fix structure of ring, then we describe map, or if we choose particular type of map or fix these map, then to find out a ring structure. Okay, so these are things we discussed. So that means we are talking here, if this habit and the habits, what we can say about the structure of D, G, and R. So these are the new just like and another problem in this same direction, what happens fixed integer and R, B, ring. We are talking. So you notice before we are always talking about prime or simultaneous. Now, once when the idea of prime ideas came into the existence, this is the result for arbitrary ring. That means more everything. Okay, so this is the benefit when we consider the prime ideal bit derivation. Okay, so of course this prime ideal and D and capital D are and derivations which trace D and G. So if Gx is X belongs to P, then again same portion, but we can say about the structures of the maps as well as the ring as well. And this is the same answer problem in the same sequence. This one, then we just here, if you look over, we take Jordan product. In fact, these two structures not we have same means Jordan product and Jordan product. Okay, but in certain class of rings, these two structures are coinciding. This is so. Which are the structures where the Lee and Jordan product coincide? Anyone of the student? Yes, please. I hope if you remember my lecture, I already answered before. So that's why I'm asking this question. Okay, now remember. Think where x equal to minus x. This is the class of rings where these two structures coincides. Okay. So with these open problems, we are going to conclude our discussion today's discussion. And thank you so much for your questions to listen to this talk. And now finding this in my link. And if somebody is interested, please go ahead and you can download these papers from here. And whenever you go for searching like American Math Society or means math review, then you always write down Ali Shakir. So you find only my paper. If you write down Ali Shakir, S Ali, then you may have some other paper. So we specify this is my math science name, Ali Shakir. Put over here, and you can find out the center. So thanks once more for your questions to be. Yeah.
I think Musa has special needs.
So what is question of Musa? Yeah. Excuse me, Professor. Does this mean biology mapping is the same as distributive binary operation, and semantic mapping is same as commutative binary operation? Not always, Musa. Musa. I think he asked a question then. Anyway. Ask any other question, please feel free, because this is time to you.
Prof, in definition, we know that if we have two composition of the equation, if the composition is the equation, then the composition its definition should be zero.
One of them.
Yeah, one of them should be zero. And in the PD derivation, we also has
Which derivation?
B derivation. The derivation.
By derivation, yeah. Yeah.
Derivation, we also have that
Yeah, that kind of derivation. Yeah, right.
My question is, how about the characterization of composition of generalized derivation or generally? Do you have
Far more, because the idea is same. However, when you have changed the ring, okay, then you find more good characterization. Like for composition of two generalized derivation has similar observation, okay. But when we dealing functional identities, the paper by V. Hawala, no doubt, paper by V. Hawala, there is full paper for such characterization, lot of beautiful results under certain conditions, okay, when the composition of two generalization is a derivation. Okay, paper by V. Hawala, communication algebra, and another paper by TKD, generalization of faithful rings. So these two papers give the whole background about this idea. It's more than the inference is more.
Thank you very much.
One of your example, you mentioned that you asked a question, but you didn't answer. Why in the one of your example you use C, the complex number, the matrix over C? You didn't answer.
I asked question, I did not answer because I want to know. Some of them may ask why this field is important. You know, in case of examples always depend on situation because according to your need. Okay. So in all the cases, because we use sometimes conjugation. So in case of the complex field, we have a good work in the state of conjugate elements. So that's the only answer for this. But the sake of our requirement is not specified. You may take the other number. Yes. Means we will find this in the, I think it is good example to mention. There you can construct or some construct more example in other. And field is, and second part, because C is commutative ring. So this is the another benefit. Okay, every field is commutative ring. So this is another benefit. That's behind of the things when we are making calculations. So we use the commutative. This is the exact answer for that.
Just related with involution.
Sorry?
Related with involution stuff.
Involution, yeah. Because the role of involution in complex field is very important. Mentioned that conjugate is one best example for that. If we define Z star, that means the conjugate of that. So this is one of the benefit we get in relation. Also, such things we had is our computative. So many things in that particular field has, not other has. Yes, any more? Some more. I think. No, they just some minutes. So, anyone have more questions? You are welcome, because this is the not talk in the conference. This is usual discussion, so we have enough time to discuss. We're not in a hurry.
Yes, I have another question. You mentioned that, for example, in the first case, from derivation into symmetric derivation, you show us the connection. So from this you can produce this, from this you can produce this. Right? How about the another properties? It means that if you have certain properties in this case, also we can have same properties in the another.
Go on particular form, then I can send you. Please reach the example of them.
Yes, from derivation to symmetric opposite. From this derivation to bi-derivation. Can produce it another.
No, I mean, upon your, that means how to form the bi-derivation with the help of derivation. So bi-derivation means derivation in each source. Okay, so if I have a derivation, you always construct by derivation,
Yeah.
because if you define in such way when both the conditions are satisfied, like symmetricity and like we defined, I remember somewhere capital D x1 x2 is equal to small d1 x1 small d x1 and small d x2, where d is the derivation from R to R. So if the derivation, then after it satisfy all the properties that is identified and is also derivation in first argument, and you need derivation first argument. Similarly for D2, if this is derivation, it's a definitely derivative on the second argument. So you can combine and make it a derivation by derivation.
I mean, it is automatically the properties in derivation transfer to the bi-derivation.
Yeah. But you know, why derivation is always not derivation? That's another question. But derivation, you can generate derivation. Because if you look on the definition, D from R to R, even for by definition, D from R plus R to R. So it's not very same thing, but we can one way and another way generate by derivation with the help of the value notion. That is the idea.
You know? Okay, thank you very much.